give us a short introduction to your research?
Absolutely. So the research that we have just performed here was called Save the Oxygen Molecule. And you may think that the oxygen molecule doesn't have to be saved, maybe because nobody thought that it was in danger. So I will start by explaining a little bit the overall picture. So the type of research that we do is really trying to understand phenomena in terms of electrons and atoms, how they are moving. And the idea is that everything around us, I mean the objects and the air we breathe, our bodies, everything ultimately depends on how electrons and nuclei are moving. So that's the whole thing. But to do that, you have to study things on very fast time scale, because the electrons and the nuclei move very fast. So we always talked about the femtosecond time scale, and that means really that very, very short times. So if you think about your everyday experience of time and the events that you see, and compare that to the age of the universe. So the astrophysics always want to see these very, very long time scales. So if you compare everyday time experience to the age of the universe, it's many times longer, but the times we are looking at are as many times shorter than what we are sort of experiencing. And on that time scale, we want to like to see this drama with the oxygen molecule. Oxygen is then taken as an example. I mean, it's a simple system where you can maybe understand what's going on this time scale. So the thing that we do, we're with these photons that we can get here from SQS, we can put the molecule in a very specific state where it should be destroyed, that these two atoms would just go apart, O2, and it will just dissociate on this very fast time scale. But with these photons, we may have a chance to save it, so that before it dissociates, you have another pulse coming and stimulates the emission so that it will still be intact. So this is a kind of a theater that we really like watching, and to do that we use this instrument. So we look at we monitor the signals that come out, and they give us then the information about did we save it or did we not save it. Then we are very much dependent on the machine people here. They had tried to provide us with very, very short pulses, very controlled pulses, and it's really a challenge that we put the machine people on to do this.
How can the SQS instrument help you learn more about Corhole state dynamics observed in the RIXS spectra of oxygen?
It's really the SQS is really the only place in the world. There are also efforts at LCLS in Stanford, where they may have similar possibilities, but otherwise this is unique, and the combination with SQS and this instrument is really unique. That is nowhere else that you have that. So I think with the intensity and the pulse properties here, it's the only way to save the molecule. And I should say also, it's not only that we like watching this theater. We do. I mean, it's exciting, really. It's drama. But of course, it's a more general information that you really learn more about this ultra-fast, what the atoms and molecules are doing on this very short time scale, where most of the properties, or all properties, of matter sort of evolves. So it's really a very general thing, and the oxygen molecule is chosen because it's simple, basically, so that we can understand the details.
How can learning more about oxygen Corhole state dynamics help society in the future?
In general, I mean, this is a quite difficult question because this is basic research, certainly. So it will not immediately help the world to save the world. And the general idea is to learn more about these fundamental interactions that ultimately determine the properties of, I mean, not only of what we see around us, but also modern technology and how things are moving. But I can mention one example perhaps where it and often this basic research is really, I mean, you don't see the applications, but we actually the studies of the oxygen molecule recently, it was shown in batteries that when you recycle batteries, actually oxygen molecules are formed. Not that they want it, but that's a thing that destroys the function of a battery when it's cycled many times. And using methods like this, one can really see that the oxygen molecule is there, and also that it's slightly bound to these cathodes that are in the battery. But I think, I mean, this is a sort of a surprising direct application in battery research, which might have to do then later with how to refine the batteries, but it's a long shot, and I think it's not really fair to say that we will immediately be useful, but knowing more about this dynamics on this time scale will eventually lead to a better understanding, perhaps of chemistry in general, and also solids. How I mean, it all depends on how the electrons are moving.